The first model which I'm going to consider here is a moving average. So moving average, just like weighted moving average, depends upon what we call the value of n. What's value of n? Value of n is basically the selection of lags for a particular time series forecasting model. In this case, the moving average. So let's suppose if this is the actual data, which is right here. So we basically got uh, historical data for 10 past periods. And based upon this historical data, we are supposed to forecast for time period 11 using a particular forecasting model. In this case, it's a moving average. So let's suppose if I take the 2 periods moving average, so this means that the n value should be 2, which means that we should have 2 lags in this particular model. Now, what are lags? Lags are simply the previous value. So in moving average, if we consider n as 2, so this means we need to consider 2 previous values and then take its average. And the word moving simply signifies that as we move along, then the average should also move along with the calculation. So it's more of a dynamic mean which we are calculating. So in this particular case, if I were to start the calculation from time period 1, so this means I need in moving average we need 2 lags. So by lags I mean uh, a subscript t minus 1, that's the first lag, plus a subscript t minus 2, that's the second lag, and then divided by 2. So this particular model is a moving average model where n is equal to 2. So we can call it a 2-period moving average. Now, so if it's a 3-period moving average, so this means that the n value should be 3. And instead of 2 lags, we are to consider one another lag, which is a third lag. And in such case, we need to divide it by 3. Now, in this case, we got 2 lags. So what's a lag, and how can you know about a lag in a particular estimation when you're using Excel? So whenever you put a equality sign, so this equality sign means that whatever value you got in this particular row where you put an equality, that becomes the current time period, that becomes the current value, that even becomes the current forecast value, and so on and so forth. So uh, previous to this particular value would be a first lag, two previous period would be a 2 lag, and a 3 lag, and so on and so forth. So if I were to take 2 lags, so I don't have any lag if I start calculation from here. Now, so if I go to time period 2, now in time period 2, of course, I got this is current actual value. So this 100, the value at the time period 1, that would become 80 minus 1 first lag. But since we are using 2-period moving average, so I don't have a second lag. So this means if I don't have a second lag, then I can't apply a 2-period moving average. So this means I need to start calculation from the third time period. Now, when I start the forecast estimation of the forecast value from the third time period, so this means this is current actual value. So this value right there is 80 minus 1, the first lag, plus 80 minus 2 is this value right there. That's the second lag, and all you need to do is just divide it by 2, and you got a forecast value for time period 3, which is 102.5. Now, if I move towards the next time period, which is a fourth time period, and I want to uh, estimate the forecast value for time period 4, for which actual value is 115, then this 115 is ET, current actual value. So behind that is 110. This is the first lag, ET minus 1, plus ET minus 2 is 105. Now, you can notice something, that when we move from time period 3 to time period 4 to estimate forecast value, we skipped one value, and that is 100. So if I consider this one, so for that, we took the average of 100 and 105 for time period 3. But for time period 4, when we did that, so it's a 105 plus 110 divided by 2. So we skipped that 100, and that's why we call it a moving average. So if you keep on following the same pattern, I'll simply drag it down. So the forecast value, considering 2-period moving average, is 133. Now, so for time period 4, these two values, for time period 5, these two values, so these two values are skipped. So similarly, for the last time period, which is 11, for which we are doing a forecast, it only considered 134 and 132 for a mean. So that's why, because of that factor, the average is basically moving from the previous observations to the more current observations. So now this is the forecast value. Now one could argue that we can directly estimate this value right here. Of course we can do that, but when you estimate a forecast value, then after estimation of the forecast value, we need to also estimate the forecast error. So if we were to just ignore these values right here, and we simply estimate this forecast value, then how can we estimate error? We cannot. So because of that factor, we tend to estimate the forecast value for the previous period for which actual value is already there. And now, why is that? Because we discussed in your lecture that forecast error, which is E subscript T, is simply equal to actual value, current actual value, minus current forecast value. That is a forecast error. So for this purpose, uh, we tend to estimate values other than the one for which you need a forecast in order to summarize the accuracy of a forecast model. Now, let's estimate the accuracy, or let's summarize the accuracy of this particular forecast model which we used, which is a two-period moving average. How can we do that? So for that purpose, we discuss a particular model, and that is what we call a MAPE, which is mean absolute percent error. So what's mean absolute percent error equal to? Mean absolute percent error is just the estimation of error, which is actual minus forecasted value. Once we do that, some errors would be positive, some would be negative. So overestimation and underestimation, which we discussed in one of your lectures. Now, the next step is to uh, take absolute of the forecast error. And then the next thing which we need to do is simply divide it by actual value to come up with a percent change. And then we need to add up all of these values and divide it by the number of errors which we estimated. And this particular mathematical equation gives you the value of MAP. So MAP gives you the forecasting error in a particular forecast model in percentage form. Now let's apply that quickly. So this is that model which we use to be removing average. Let's estimate an error in that. So what's the error? So we'll first need to calculate ET. So for that, I cannot estimate error for the first two periods. Why? Because we got actual value there, but no forecast value. And forecast error is simply actual value minus forecast value. So we'll start estimating forecast error from time period 3. So this is actual value. We subtract from that the forecast value right here and just drag it down till time period 10. And these observations are basically your forecast errors. Now, uh, similar goes for the 11th period where we don't have actual value, so we cannot estimate a forecast error for that. Once we estimate that thing, that forecast error, so we need to take absolute value of that. What's the purpose of absolute error? Absolute error simply estimates, simply converts the negative forecast error into positive. But as you can see, all the forecast error is positive. By the way, in forecasting, we call such situation as a occurrence of what we call an error bias. Consistently, we are making our forecast model is giving us a positive error. So a good forecasting model should have both overestimations and underestimations. So both negative and positive values are supposed to be there. And what's the impact of that? Once we estimate the forecast error for this particular model, then I'll show you what's error bias in this particular case. Now, after that, when we estimate error, so that is the error which we estimated. Now we are supposed to take an absolute value. So how to take that? So in this case, it's not required, but since you have been given some data in your assignments, so maybe in that case, you might get some negative values. So it's simply the function is ABS equal to ABS, and all you need to do is select that value and click enter, and see there is no change in that because these are all positive value, and that's about that. Now after that, we need to divide this absolute error value by actual value. So now we are moving towards the third step of MAP calculation, which summarizes the forecasting accuracy of a particular forecast model. So we are dividing the absolute error by actual value right here. So once we do that, we'll determine the percentage of error at each point. So this is absolute error, and we are supposed to divide that by the actual value right here. So if we do that, so for the first one, we got a forecast error of 6% and so on and so forth. So if we drag it down, this is the error. These are all the errors of all those time periods for which we got forecasted and actual value both now. After that, the next step is to add all these terms together. That is where the summation comes into play. So I'll write here sum of all the quotient of absolute error and actual value. So it's equal to sum, and we need to add all of these, and that's the sum of all of these values, which we estimated in step number 4. Now for the next one, we need to come up with a value of n. So remember that n is not the number of observations. N is basically limited to the number of errors which you estimate. So in this case, if we say equal to count and the errors which you estimated right here. And for the next step, in order to estimate MAP, all we need to do is just divide this value by that. And in this particular model, we got a forecast error of about 4.6%. So if we convert that into percentage, it's approximately about 5% or 4.63, considering decimal points. Now, the next thing I told you about the error bias, right? So if we plot the actual value and forecasted value together, so it would be something like this. So here you go. That's the orange line right here. Basically, these are the forecast values, and the blue line is basically the actual value. So this means in each case, actual value is greater than the forecasted value, and the gap between the blue line and the orange line identifies that error. And you see there is no overlapping between the orange and the blue line, and this signifies that we basically got an error bias in this particular case. Now. Uh, that was a moving average which we discussed. Now let's move on towards one another model, and that model is weighted moving average. Now weighted moving average has the feature of an average. It is of course a moving average, but there is one other unique function that is in weighted moving average, we weight different observation based upon the model which we are using. So in this case, let's suppose if we are considering weighted moving average where n is equal to 2. What does that mean? Uh, that again means that in this particular model, we got about, so 2-period weighted moving average, 2-period weighted moving average. So the mathematical representation of this particular model would be, we got the first lag. So since it's n is equal to 2, so this would be a 2-period, 2 lags plus at minus 2, that's the second lag. But then again, in this particular model, we multiply weights with it. So that's the first weight, and we got a second weight, W2 right here. And then we divide it by the sum of W1 and W2 weights. And so now, what is that weight all about? So for convenience, if we say it's a 2-period weighted moving average, so we'll write 2 in a more of this form. So 2 is the highest, and after that we got a 1. So what if this was a 3-period? So we would get a 3, 2, 1. So consider these values as weights. So this means the first lag should get the weight 2, and the second lag should get the value of the weight of 1. So 2 plus 1, and basically the weight right here is 3. So this is how weighted moving average is managed. Now remember that whatever weighting we use in this particular model, the sum of all weights should always be equal to 100. And what do I mean by that? So the total weight right here is 3. So if I say 2 divided by 3 plus 1 divided by 3, and it's always equal to 1 or 100%. Similarly, if I'm considering a 3-period moving average, so this means the first lag would get the value of 3. The second lag would get the value of 2 weight, and the third one would get a weight of 1. But the sum of these weights is 6. So then again, in this case, we got a value of 1 or 100%. So no matter what weights you use, this is one method of weighting observation. The sum of all weights should be equal to 100%, I mean their division. Now, so this begs the question. So what if instead of writing 3 to 1, what if we can weight it like this? So for instance, in this particular case, if I say that we need to give about a 70% weight to the first lag, then how much weight is left? We got basically a 30% weight left. So we'll give that a 30% weight. So 30 plus 70, and that's a 100%. So that is one another way. So how can we do that? We can simply multiply 0.7 with this lag and 0.3 with this lag. In such case, we are only 2 divided by 1, which means that in denominator we got a 1. So if the weighting is in a decimal form, 0.7 or 0.3, so one another example, what if we weight this first lag, let's suppose a 0.6. So this means we are left with 40% of weight. So we'll give that second lag a 0.4. So when we sum it up, we basically got a weight of 100% or 1 in decimal form. Now, this is one way of weighting. Uh, in this particular assignment which I gave you, the weighting regime which you should use is just considering 2, 1, 3, 2, 1, 4, 3, 2, 1, and so on and so forth. So if this is the model, weighted moving average, so how can we estimate a forecast value using this model? So the same rules apply right here. In order to forecast, we need at least 2 lags. And for 2 lags, we need to start the estimation from the third observation. And in this case, I'm starting with two brackets. So the first one, the first lag, I'm giving it a weight of 2, which is 105. That's the first lag. Added with that, 1, we don't need to write 1, but just to show you. And then the second lag. And bracket close, and divided by the sum of the weights, right? So 2 plus 1, that's a 3. And that is how you come about, you can estimate the value of weighted moving average using 2 periods. Now you see there's a considerable difference between, there is a slight difference between this forecast value and that, and it's somewhat in decimals, right? So what if instead of that, we estimate the forecast value for 11 period using a 3 period weighted moving average. So that is again weighted moving average, but now I'm taking the value of n as 3. So this means now we need to have 3 lags. So for 3 lags, I need to start the calculation for from the fourth period, right? So this is equal to bracket, first weight should be 3, and 3 should be given to the first lag, which is 80 minus 1 right there, plus 2 into 80 minus 2, the second lag, plus 1 into the third lag, which is 80 minus 3, and we need to divide all of that by 6. So in that particular case, the forecast value is about 132. Now, in the first model, which was moving average, we estimated the forecast error. So in this particular case, a moving average that is 2 period, we got the forecast error of about 5% or a 4.63 in decimal, right? So that was the forecast error. For the second model, which is weighted moving average, where it's a 2 periods, let's estimate that error. So in this case, I'm just simply going to get rid of these values. So I'm going to change this particular cell right here. So instead of considering that value, I'm just going to shift it to this one right now. Then click enter and just drag it down. And you see you'll get a forecast error. So let's just check it. So this is correct, and so on and so forth. So you see instead of the 2 period moving average, now we are considering 2 period weighted moving average, and you see the forecast error in this one is about all we did was just change the size, right? And the forecast error in this particular model is about 4.9% or about 4%. So 4.09% is the forecast model. So in this particular case, which one is the best model? So of course, the 2 period weighted moving average is the best model. Now, similarly, if you want to estimate the forecast error in the third model, which is a weighted moving average using 3 period, so what would be the forecast value in this particular case? So once again, we need to change the cells. So we need to consider, so this one is missing, so I'll go to the next one. And instead of the 2 period, we are going to move towards that one. Click enter. We need a slight adjustment in this data. We are supposed to get rid of these particular observations because we don't have a forecast value right here. So we'll just get rid of that. And similarly, we need to adjust the count value as well. So in this case, we estimated about six errors or 7 errors. Yes, that's the 7 errors which we estimated. So in this case, our forecast error is about 4.89%. 4.89%. So you see, in these three forecasting models, one of which is a moving average, and two of those is basically a weighted moving average. The best performing model is the 2 period weighted moving average. That gives us the least value of MAP, and that is how you select. So a best forecast model. So you go on, you estimate the value of MAP. So the model with the least amount of MAP is the best forecast model. So least value is basically preferred. More value the MAP. So this means that the forecast error in this particular model is more. Now,